Okay, chemists, in this lesson we are going to start to look at how to put the reactions we've been learning together back to back to do some more complicated syntheses. Remember, the theme of this unit has been the alcohol functional group. We've been able to make alcohols from organometallics, reducing carbonyls, or do the opposite of reduction and oxidize them back up to other carbonyls. And now that we have organometallics, we have access to a whole series of carbon-carbon bond forming reactions, so we can make molecules that are a fair bit larger than any of the other molecules we've made in the past so far this semester. So let's try the first one. Here we have a hydroxy ketone, and it apparently looks like we want to keep the tertiary alcohol intact, but convert this ketone into a different tertiary alcohol. Now, ketones plus Grignards, or any organometallic, will give you a tertiary alcohol. But remember, organometallics are incompatible with pre-existing alcohols. So the point of this first one is to actually show that we have to protect this other functional group off on the side. And this was on one of the homework problems on your recent lessons, to turn the alcohol into a silyl ether. So I'm actually going to do this synthesis just in the forward direction, because all that I see we need to do is protect this tertiary alcohol, add an organometallic to the ketone to make this tertiary alcohol, and then deprotect the original tertiary alcohol. So let's do that right from the starting material. The protecting group we've learned for alcohol protections is TBS chloride, and usually have some kind of base to go with it, an organic base like triethylamine. And that will convert the OH into an OTBS. Remember, that is a silyl ether. The rest of the molecule is along for the ride. Now we can do an organometallic addition. Looks like we need to bring in a phenyl, so I'm going to use phenyl Grignard. Step 1, phenyl, MgBr. Step 2, H+. You can remember how that works. The phenyl acts as a nucleophile, attacks the ketone, sends those electrons up, they eventually pick up an H. But we don't draw curved arrows on top of a synthesis problem. We just write out the steps with reagents and intermediates. Curved arrows are really reserved for mechanism, arrow pushing problems to show how bonds break and form for one reaction or one tandem reaction maybe. But here we're not doing that, so we're just going to show what this turns into. So the left half of the molecule is the same. I have a silyl ether. The right half is now a tertiary alcohol. The methyl that was part of the ketone is still there, but I have a new carbon group, and it's this phenyl ring. Almost done. I just need to get rid of that TBS protecting group, and the way you do that is you use a source of fluoride. Fluoride is tetrabutyl ammonium fluoride. Fluorine forms a very strong bond with silicon, so it will actually strip off that TBS. You do it usually in the presence of water, something protic that can put the H back on, and then you'll end up with two tertiary alcohols. One new one from the phenyl addition, and one that was there from the beginning. So 3 steps: protect the alcohol, add the Grignard, deprotect the alcohol. Done. B is not as straightforward. B has a couple more steps involved, but this is an opportunity for us to look at retrosynthesis. Retro meaning going backwards. So before I consider what to do with the reactants forward, I'm going to just look at the product and say, how do I make that thing? The good news is this is an epoxide, and there's really only one way to make an epoxide that we've seen, and that's from the MCPBA epoxidation of an alkene. So I'm going to write a retrosynthesis, which is this double arrow, and draw the alkene that would give me this epoxide. If I had this alkene, I could get that epoxide. So how do I make an alkene? Well, alkenes can come from dehydrations of alcohols. And I've got 2 choices. I could either have an OH on that carbon up there, or an OH on that carbon down there. And for this case, I'm actually going to draw both. And then maybe I'll consider which one makes more sense after we see them. So I've either got that alcohol or something very similar, but the OH on the other carbon. Either of those could be used in a dehydration, where you would predict you'd get the Zaitsev alkene, something like POCl3 or just acidic hydrolysis and heat would give you that more substituted tetrasubstituted alkene in each case. Just for good measure, you could actually have a bromide and predict a Zaitsev E2 elimination as well. So if you were doing this and you were thinking go back to the bromide to do an E2, that's not incorrect. We just don't have any ways of selectively making specific bromides like that, so it might be tougher to get to that intermediate than either of these alcohols. At this point, I'm going to take a look at the starting materials, and I see a 4-carbon piece and a 5-carbon piece that I have to somehow bring together and make one of these two tertiary alcohols, which means I would love to make the carbon-carbon bond right there, or the analogous one on its neighbor right next to it. So how do you make a tertiary alcohol? Go back to our organometallic lesson. Those come from organometallics and ketones, which means I can actually just work with one of these. This is a tertiary alcohol. I'm actually going to make some space and draw another retrosynthesis where I imagine making that bond. I'll just draw a dotted line through it for now. And that means the upper half would come from a ketone. I'm drawing it kind of ridiculously, but intentionally to show how it forms from this lower half. And what did this lower half used to be? Just an anion? Well, almost. It was the organometallic. So something like a Grignard. If I can get to this Grignard from my starting alcohol over there on the left, I can react it with this ketone, which I can also make from my starting alcohol. And then I'd get to the tertiary alcohol that I want. Let's keep going backwards though. It's always a good idea to go backwards until you feel really confident that you've gotten all the way back to the starting material. How do I get to this Grignard? Grignards are easy. They come from the halide. And actually that halide is one step away from the starting alcohol that we're given in the beginning. That's the PBr3, a way to convert an alcohol into a bromide. So there's a perfectly good retrosynthesis. Now let's go back and write it out in the forward direction. So separately, I'm going to convert this alcohol into a ketone. And I'll fill in my reagents. PCC, Swern, Jones, any of the oxidations we learned in the previous lesson would do that. Separately, I'm going to convert this alcohol into a bromide. It's secondary, so I'm going to use PBr3. HBr might work, but that's not the best carbocation, so I'll predict PBr3 is just as good. Then I'm going to convert that bromide into the Grignard. That's just elemental magnesium, Mg neutral. You get cyclopentyl Grignard. Now I'm set up to react this with the ketone. So step 1, the ketone we just made. Step 2, hydrolysis, aqueous workup. Then I have my 5-membered ring, new carbon-carbon bond. All 4 carbons of that ketone are still there, and now I have a new OH. So I'm intercepting these retrosynthons that we came up with a moment ago in our backwards synthesis. That was just our plan, but now here's our actual answer to the question. I still have to go forward some more. I have to turn that tertiary alcohol into an alkene. So go back to earlier in the semester, we could use POCl3, that will do an elimination, or H3O plus and heat, if that's easy to remember. And then lastly, we make the epoxide. So I do that with metachloroperoxy benzoic acid, MCPBA. And there's your epoxide. Quite a few more steps than the first one, but a good review and a combination of lots of reactions that we've learned. Okay, let's do one more and then have you hit pause and see if you can try one on your own. C has a bromide, an aldehyde, and an epoxide as my 3 starting materials, and I want to make a primary alcohol. Now, just like up above, we intercepted an alcohol and we thought about making it from a Grignard and a carbonyl. I'm kind of thinking about using things like Grignards and organometallics a lot when I see alcohol functional groups. However, I notice my carbon count, this is a 3-carbon piece, another 3-carbon piece, and a 2-carbon piece. So when I put those together, I spy a 3-carbon piece here, another 3-carbon piece here, and a 2-carbon piece there, and that's probably where those 3 functional groups entered this molecule. So how do I make an alcohol from something like an epoxide? You can also use an organometallic. So going backwards, I'm going to think about actually making this bond. From an organometallic that looks like that, and an epoxide. Epoxides are quite clever little molecules because when you react them with organometallics, you end up with an OH 2 carbons away from where the addition looks like it took place. So that bond that I'm breaking, going backwards, effectively the bond I'm making, puts the alcohol an extra carbon away. It's a little harder to see, I think, in the retrosynthesis, but they're really useful. So the epoxide we've got, how do I make this Grignard? Well, that comes from the bromide. And I'm going to actually skip a retrosynthesis step and say bromides come from alcohols. I know that this comes from the bromides, I'm going to write it. How do I make an alcohol? Another organometallic addition and another oxygen-containing electrophile. Not the epoxide this time, but maybe that aldehyde. If I go back to the beginning, I have a nice 3-carbon group that could become a Grignard, and then I have an aldehyde that I could react with that Grignard. In fact, if we do that, you get this alcohol. So I've got a much shorter retrosynthesis here because I already see what I need to do in the forward direction. So let's write that out going forward. First up, treat the bromide with magnesium. That'll make propyl magnesium bromide. React that with the aldehyde. So we've got a 3-carbon Grignard and a 3-carbon aldehyde. We're going to get a 6-carbon molecule. 1, 2, 3, 4, 5, 6. And our alcohol is right there. We just made that bond. And that actually is that alcohol up there. So we have intercepted the molecule we're trying to make. I just drew it a little differently. And now we need to turn that alcohol into this big Grignard that I want to react with the epoxide. So first convert it to a bromide, PBr3. Just converts the OH to a bromine. Turn that into a different Grignard. And then lastly, react it with an epoxide. Step 1, this simple 2-carbon epoxide, followed by an aqueous workup. That'll get me my 6 carbons, new carbon-carbon bond attached to another carbon with an OH coming off of that carbon. Now that's drawn differently than the molecule that we have up there, but it is the same. Check your carbon count. You've got a tertiary carbon right there with a propyl, an ethyl, and a hydroxyethyl all attached to that one spot. There's that tertiary carbon with a propyl, an ethyl, and a hydroxyethyl. This is exactly what we want. So those are the first 3. What I think you should do now is hit pause and then challenge yourself to do this last one. Here we have an alkene and an ether. Do the same thing, go backwards. How do you make this functional group? This time I'm challenging you to use only propene as your only source of carbon. And if you do a carbon count, you'll see how many times you're going to have to use it, at least. So hit pause and try that now and come back and see how you did. Okay, so if you did a retrosynthesis, my first backward step would be to notice that this is an ether. And that's useful because there's really only one way that we've seen to make an ether quite regularly, and that's the Williamson ether synthesis, and that would come from an alcohol doing an acid-base SN2 reaction on an alkyl halide. So I have this 5-carbon alcohol and this 3-carbon bromide, both of which I need to make from just propene. The bromide we can do. The bromide I could do a non-Markovnikov addition of HBr to just propene. So we're there. The alcohol is a little bit tougher to see. But remember, we're making alcohols from things like organometallics and aldehydes or ketones or epoxides. So I could imagine making this carbon-carbon bond from a 2-carbon aldehyde and a Grignard that looks like that. That's called allyl Grignard. And allyl Grignard could come from allyl bromide, which we can actually make using a radical bromination, an allylic bromination of propene. And then what about this 2-carbon aldehyde? Well, that can come from the ozonolysis of the same starting alkene. So we successfully got back to propene for every single one of these. Now we have to string it together and add our reagents and write it out as a forward synthesis. So many things have to be done. First, I'll take propene and I'll do an ozonolysis. That's ozone, followed by a reducing agent such as triphenylphosphine. That will turn this into your aldehyde. I'll just draw it on its side so you can see how that happens. Next, we need to make that Grignard. So if I take propene again and just do a radical halogenation, either with NBS or elemental bromine and photochemical conditions, you'll get the allylic halide. I need to do a couple of other things to that. I need to convert that into a Grignard. That'll give me allyl Grignard. We can then react that with our aldehyde, which we already made. That gets me my 5-carbon secondary alcohol. All that's left is to do the Williamson ether synthesis with this bromopropane, which means I actually still have to show how to make bromopropane. So I'm going to go back to the very beginning, squeeze it in as another beginning reaction. This makes this a very non-linear synthesis, which is nice in the laboratory. If you have a synthesis that brings multiple steps together in a later stage, if anything goes wrong in one path, it doesn't ruin the whole synthesis. They call that a non-linear synthesis, as opposed to one continuous snaking synthesis from start to finish, where if you have anything that interrupts the assembly line, it all goes down. There's the bromopropane, and now we're going to use that in a Williamson. The Williamson synthesis involves 2 steps. It's usually sodium hydride that will do the acid base to give it the alkoxide, and then the SN2, in this case with bromopropane. So I get a new oxygen carbon bond, and that's our product. So starting with just propene, we made this ether with the allyl group hanging off of the alcohol carbon, what's now an ether carbon, and that's a nice refresher of a lot of reactions we learned earlier this semester, and then also some new ones in this unit. Okay, there's plenty more syntheses to practice, but that's a good place to get you started. Try some more practice, and we'll assess ourselves on this soon enough.